Time for us to be a little bit improper. We're going to talk about improper integrals, which means integrals involving infinity. And as with many things that involve infinity, sometimes things are a little bit counterintuitive and we must tread carefully, which means we have to do practice. The more we practice, the better we are getting at avoiding pitfalls and making mistakes. So do as much as you can, because the more that you do, the better you're going to become. If you're following along with this video, make use of the pause button. If you see a problem, pause. Try to do it yourself. See how far you can get. And if you ever do need my help, I'm here. You just need to unpause. And away we go together and enjoy our time in calculus. Well, let's begin. Our first problem. Calculate, whatever that means, the integral from negative infinity to infinity of 2x over x squared plus 1 dx by doing the following. So we're going to do it twice. Oh, all right. Why do we need to do it twice, right? If we do it once, that's the answer, but all right. Now the actual integral itself, it's not a bad integral. 2x over x squared plus 1. Look at it. If we just were doing this integral, don't think about it as an indefinite integral. What do you see? Well, if you set the bottom to be u, then the top, 2x dx, would be du. So it's really of the form 1 over u du, which means it's a natural log. So we get natural log of x squared plus 1. And of course, plus c. All right, well, great. So we're almost done, right? So part A says, hey, what do we get? Well, it's going to become our limit as b goes to infinity of, and when we integrate, we have the antiderivative. So it's natural log of x squared plus 1 from negative b to positive b. Okay, well, great. So that's our limit as b goes to infinity of log b squared plus 1, that's if I plug in positive b, subtract log of b squared plus 1, and that's if I plug in negative b. Well, they're equal. They're equal. So that becomes our limit as b goes to infinity of 0, which is 0. All right. Woohoo! Nice. It's 0. And in fact, it makes a lot of sense that we should get 0, right? Because what kind of function is this? It's a little odd. It's an odd function. And so when you have an odd function, we expect, we integrate from, a minus something to a plus something, that symmetry says cancellation. You get 0 out. All right. Well, so that's the answer for part A. Get 0. Now for part B, notice, well, it's very similar. The only difference is negative b to 2b. But notice it's still going from a very large negative number to a very large positive number, and it's getting bigger and bigger and bigger and bigger. So in essence, it's still integrating from negative infinity to infinity as we take our limit, right? Okay, good. So intuitively, what should we get? We should get the same answer. Let's find out. So what do we see? Well, we'd have a limit as b goes to infinity. It's the same function, so same antiderivative. And we're going from negative b to 2b. So that's our limit as b goes to infinity of natural log. And when we square it here, well, that would be 4b squared plus 1 minus natural log of b squared plus 1. Okay. They don't exactly cancel, but that's okay. That doesn't mean all hope is lost. We just have to be a little careful. Now, notice we have a subtraction. When we have subtraction in logs, that becomes division. So that's log 4b squared plus 1 over b squared plus 1. And now, here we go. We can work our way in, or rather, maybe I should say work our way out. what happens to the inside? Well, the inside, 4b squared plus 1, b squared plus 1, as you let b get large, the plus 1s, they don't do anything. They're insignificant. And so really, it's like 4b squared over b squared, which means the inside is heading towards 4. So what do we get? Well, this is going to log of 4. And so what's that? It's log of 4. Now, what's happened here? Let's take a second. We're actually done with the problem. We've done this calculation as requested. And we can either sort of shrug and say, okay, well, whatever, move on. Or we can say, wait a second, something seems fishy here, and sort of gain insight. I'm of the belief we should pause and gain insight. So what's fishy here? Well, what's fishy is in both part A and part B, we are essentially going from minus huge number to plus huge number. We are. And so as we take our limit, it's in both parts A and part B, we are trying to capture the integral from negative infinity to positive infinity. So why did we get different answers? Shouldn't we get the same answer? And what do we learn because we didn't get the same answer? Well, here's the thing. This is why you have to be careful. So one of the things that we're going to learn is be careful. Now, if you graph this function, and we'll do it really quickly here, what you'll see is you have something that looks like the following. And it does this kind of behavior. It's not so important that you know it exactly. But the key here is that if you look on the plus side, you say, okay, how much area is in there? Well, it turns out it's infinity. Whereas if you look at the minus side and say, well, how much area is over here? Well, it turns out that what you get is minus infinity. And so the total area is what you get if you add those two together. So it's infinity minus infinity. And when you see infinity minus infinity, this is indeterminate. In other words, there's not enough information for us to figure it out. And it could be anything. And this goes to show you that, yeah, when it's indeterminate, you have the ability by how you go about measuring things to change the answer. So that's why you have to be careful when you have infinities involved. So we can't just blindly say, oh, let's just take everything as one big piece and it all works out and life is good. Because if there's multiple things that involve infinity, there can be some hidden underlying shenanigans, let's say. So this is why when we talk about doing improper integrals, it's very important to break it into parts. For each infinity, it gets its own part. And so that's the moral for this problem. Be careful, break things into parts, one part at a time. All right, well, good. A nice warm-up problem. So let's keep going. Our next problem. Find the integral from negative infinity to positive infinity, 1 over z squared plus 1. It's kind of similar to the last one, right? But a little different. There's not a 2z on top. So, what do we do? What do we do? Now, we say, hey, hold on a second. We have two infinities. So, properly, we should go about this by breaking this up. So, this would be from minus infinity to 0 of 1 over z squared plus 1 and plus 0 to infinity of 1 over z squared plus 1. So that way, on each part, there's only one infinity involved. Now the function itself never blows up, so that's the only two problems we have. And now we say, okay, well, what happens to these? And, well, okay, so the first one does what? Well, the integral of 1 over z squared plus 1, that's a nice one. It's arctangent of z. And we're going to go from minus infinity to 0. And the second integral, well, it's the same integral, still arctangent of z, but going from 0 to infinity. Now, it helps if we know something about arctangent. Well, to know something about arctangent is to know something about tangent. And so if you start with the tangent function, it looks something like this, where we have asymptotes vertically at negative pi halves and at positive pi halves. And now, say, look, take the tangent function and you do that flip. So you do the flip around the line y equals x. So you flip across that line y equals x, and what do you see? It transforms into our function that looks like that. And okay, so we still have asymptotes, but now they're not vertical, they're horizontal. Okay, so now we're ready to begin. And here is where we're going to be a little bit careful. Technically, we should have limits involved, but we're going to be a little bit lax and say, okay, we're not going to stress too much about having the limits. But what we do want to make sure is that we know what we mean. So what does it mean to have negative infinity? See, you can't plug infinity in. Every time we talk about plugging infinity in, it really means what's the limit as we head to infinity. So just remember, infinity is not a number to plug in. It really says what happens as you get large. So we start here. Arctangent of 0 is 0, subtract, plug in negative infinity. Well, that really says what happens to arctangent as we go towards minus infinity, and the answer is we approach minus pi halves. So we put minus pi halves. So we're using information about the asymptotic behavior for arctangent. Add to that, well, arctangent of infinity. Well, let's just plug it in. Okay, again, plug in arctangent of infinity. Okay, that really says what's happening to arctangent as we go to infinity. And what does it do? Well, it goes towards positive pi halves. So pi halves, that's when we, again, evaluate at infinity. Subtract arctangent of 0, well, that's just 0. And what do you see? You see a pi halves, another pi halves, and they combine together to give us an answer of pi. And there we go. That's it. Okay, no big surprise. That one's pretty simple. Easy as pie, right? Well, on to another one. This one's a fun one. I like this one. Find the integral from 0 to infinity of 1 over x squared plus 1 quantity squared dx. Okay, well, how would we start this problem? Now, I'm going to note right now, it is definitely an improper integral. So that is a topic for today. Remember that we said that. We're going to come to a point in a second and said, hey, don't you remember something? And you're like, oh yeah, we remember that this is improper. Okay, that's going to come back to us in just a few minutes. So how do we do an integral like this? What's the problem? Well, the problem is that plus 1, if it wasn't there, life would be good. So we'd like to get rid of the plus 1. But because it's in the denominator, can't do much. We can't do partial fractions. This is partial fractioned already. It won't get us anywhere. But there's something else. We can do trig substitution. So when we have something of the form u squared plus a squared, if we make the substitution, u is a tangent theta, then what can happen is that the u squared plus a squared can condense into a single term. So for us, because we have x squared plus 1, that says, look, let's let x equal tangent theta. Dx, well, that would be secant squared theta d theta. And, well, what else? X squared plus 1. Well, that's tangent squared plus 1, which is secant squared. See, that's really the goal. We make the substitution so that the x squared plus 1 collapses into a much easier to work with expression. All right, great. Now, let's see what happens to our integral. So, our integral becomes, well, the dx upstairs is secant squared theta, d theta. Downstairs, x squared plus 1 squared is secant squared squared. And do our bounds. So, 0. When does 0 equal tangent theta? Well, 0 equals tangent theta when theta equals 0. Now, let's deal with the infinity. The question. When we talk about infinity here, we always talk about as we go to infinity. So every time you see infinity, it's like as we go towards. So there's this sort of notion, our upper bound is going towards infinity. So as x goes towards infinity, in other words, as x gets big, what happens to theta? Well, if we think of this, we can say, hey, theta, it's like arctangent of x. Now, as x gets large, arctangent gets to pi over 2. So as we let x go to infinity, theta goes to pi over 2. All right, so that's sort of a key step there. We're going to clean this up now. Notice we can cancel off a single set of secant squared. So, woohoo, good for us. And we will have 1 over secant squared. Well, that's the same as cosine squared. So this becomes integral 0 to pi over 2 of cosine squared theta d theta. Now, remember a few minutes ago, we said, hey, our integral is an improper integral because it has infinity. How about this integral? Is it improper? There's nothing improper about it. It's very proper. Very, very. It's so proper it could be in one of those classic British dramas. It's so proper. Okay, great. So what happened? How did an improper integral transform into a proper integral? Well, this can happen with substitution. Because when you have a place where you might have, oh, it's improper because of the bounds, well, it turns out that with the right kind of substitution, our bounds go from an infinite thing to a finite thing. You can also have, and we will at some point do an example, where we have, oh, it's improper because we have an asymptote. But then after substitution, the asymptotes fly away. That can happen. And that's because what would be happening is you might have the denominator 0, but that dx would also become 0 as well, and you get some cancellation of zeros. So it's sometimes in your interest to make a nice substitution to transform an improper integral into a proper integral. No more need to talk about limits or being careful. Now we just say, great, this is an integral we can do. And because it is an integral we can do if we power reduce. So cosine squared, that's a half plus a half cosine 2 theta d theta. Well, okay, so that's 1/2 theta plus 1/4 sine of 2 theta. The 1/4 because we already have a half, and we need to divide by another 2. And integral of cosine is positive sine. So there we go. And we don't need to go back to x because we've updated everything. That's the nice thing, is when you update your bounds, you always move forward. You never look back. Full speed ahead. So evaluate 0 to pi over 2. And what do we get? Well, a half times pi over 2 is pi over 4. Sine of pi, because 2 times pi over 2 is sine of pi, 0. Plug in 0, 0, sine of 0, 0, and we're done. Pi fourths. Wow, cool. What an answer. Actually, what a beautiful answer. It's great. Wow. It's amazing that pi, which is very much we think of as, oh, it's a circle thing. And whenever we think of pi, we think of circles or sphere. We think of these nice round things. But then you see integrals like this, and like, where's the circle? And somehow, yet it shows up. What a beautiful thing. What a beautiful thing. All right. Well, still more problems to do. Plenty more problems to do. The world is full of them. So our next problem. For which p, so we're thinking of p as a number, does the integral from 1 to infinity x to the p dx converge? So this is not just, let's just do this for practice. This is actually going to be very, very important as we move forward in the course. So we need to make sure we're careful and we get the right answer now. So let's talk about the integral of x to the p. It turns out two things can happen. And what are the two things that can happen? Well, it depends on what p is. Now, the general rule for integrating x to the p, you say, add 1 to the power divided by the new power. So it would be 1 over p plus 1, x to the power p plus 1. Now, there's one case when this doesn't make sense. And you can see, well, if I have a 0 downstairs, that's bad. So this is the integral if you're not negative 1. Okay, what happens if you are negative 1? Well, then x to the minus 1 is 1 over x. The integral of 1 over x is log of x. And of course, plus c. All right, fine, great. So what happens? Well, so let's do the log of x. So the integral 1 to infinity of 1 over x dx, well, that's log of x from 1 to infinity. Now, I know here that there's only one place where we're improper, that's the infinity. And when we talk 1 to infinity, there's a built-in limit here. If you're cautious, you can put limits in. I'm not going to put limits in all the time. I am going to put them in when I need them, but generally speaking, I only need them when things get a little bit non-trivial. We'll do some examples of what that means. Okay, so let's think about what's happening here. Now, we say, okay, plug in infinity, which means what happens as we go to infinity. And what we see is, well, we have natural log. When we put a big number to natural log, it's not very big, but it's not small. It turns out natural log does go to infinity. It takes its time. It drags its heels, kicking and screaming like a young child at the mall. No, I don't want to go. Ah! But it goes there eventually. So this will head off towards infinity. So this goes to infinity. Of course, when you plug in log of 1, that's 0. Well, so that's infinite. Now, what does we mean by the phrase converge? It means really it goes to some finite value. Not that we don't consider infinity as something converging. You might occasionally hear the phrase converging to infinity, but if you just say the word converge, we mean we want a finite number. So, conclusion, diverges. Okay, so negative 1 is not a good choice. Well, now let's assume we're not negative 1, so p is not negative 1. Then what do we have? Well, we have the integral of x to p is, 1 over p plus 1, x to the power of p plus 1 from 1 to infinity. Again, when you plug in 1, you get a number. We don't really even care what the number is. We just want to know what's happening. And now we say, well, let's think about it. I have a large number raised to some exponent. So, what can happen? If I have a big number and I raise it to a positive exponent, it's going to be bigger, 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 bigger. If I have a big number raised to a negative exponent, smaller, 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 smaller. So what's going to happen here says, look, there's sort of two possibilities. If p plus 1 is positive, then when I plug in infinity, it's just going to keep getting bigger and bigger and bigger. It's going to blow up. So this is if p plus 1 is positive. On the other hand, if p plus 1 is negative, then what will happen is as we go towards infinity, this is going to get smaller and smaller and smaller. So it's going to end up being 0 minus, and when you plug in 1, 1 to the power of p plus 1 is 1 over p plus 1. And that's if p plus 1 is negative. And we know that p plus 1 is not 0 because we did that over here. All right. What's our conclusion? Well, okay, it's diverging if we're above 0, in other words, above is p plus 1, and diverges if p is negative 1, and it converges if we are p plus 1 is less than 0. So if we put this all together, we can say, aha, the answer for which p does this converge is it converges if p plus 1 is less than 0, or, to put it more simply, as long as p is below negative 1. So if p is below negative 1, we're good to go. If p is greater than or equal to negative 1, it's going to blow up, and it's not going to converge. So again, this is an important integral. So it's good that we took our time, and we have a nice answer for that. All right, well, good. On to the next one. Okay. For which p does the integral from 0 to 1 of x to p dx converge? And we're like, wait, we just did that. No, we did a slightly different problem. We went from 1 to infinity. Now we're going 0 to 1. Okay, different problem. See, the last time we had our infinity was involved in our bounds. Here, there's no problem unless we're at 0. 0 could be a problem. We might be blowing up. In other words, we might have an asymptote at 0. Okay, so we still have our same basic integrals. And so let's run through our cases. So if p equals negative 1, what do we have? Well, the integral 0 to 1 of 1 over x, that's x to the minus 1, would be natural log of x from 0 to 1, which is, okay, natural log of 1 is 0. And now, what is natural log of 0? This is where limits come into play. We can't plug 0 in. It's undefined at 0. But we know a little bit about the natural log function. If we look at the natural log function, what does it do? Well, if you do a sketch, we can do a quick sketch here. Natural log does the following. It comes like so. So when we talk about natural log of 0, we really say as our input approaches 0, what does natural log do? And we can even be more precise because we really care about as we're coming from above. So as we approach 0, what happens? Well, the natural log is blowing up, in some sense, towards negative infinity. So it's 0 minus infinity, or it's infinite. So it's diverging. All right. Well, great. What about the other case, right? We did p is negative 1. What about p not negative 1? Okay, well, let's talk about the other case. So if p is not negative 1, all right, what do we have? Integral 0 to 1 of 1 over, just x to p. And that 1 over, that's where got ahead of ourselves, right? Well, at least I got ahead of myself. You were probably calm and collected, be like, I'm not going to rush. I'm going to take my time and enjoy this problem. Okay, so we know the antiderivative. We're evaluating 0 to 1. All right, great. Well, what is that going to give us? Well, we plug in 1, and you get 1 over p plus 1. Great. And then you plug in 0. Now, here we have to be careful. So I'll go ahead and say it's 1 over p plus 1, subtract. Now, when you plug in 0, we could say, let's just approach 0. So limit as we approach 0, and we can approach it from above because it's on the bottom side of 1 over p plus 1, x to the power of p plus 1. And now we can stop and say, okay, well, what's happening? Well, it all depends on what that value of p plus 1 is. Suppose p plus 1 is positive. Well, then I have a small number to a positive exponent. It's going to be a small number. So that says, hey, this is going to be 1 over p plus 1 if our p plus 1 is large. Now, what if p plus 1 were negative? Well, if we have a negative exponent, it's like we have like 1 over. It's like it goes into the denominator. So as we get close to 0, if we have x to a negative exponent, it means that we're going to blow up. It's going to be huge. And so what we get is that it's going to diverge. So it's actually going to blow up if p plus 1 is less than 0. Now you might worry about the sign. Why is it positive infinity? Well, because p plus 1 is negative, and there's a minus there. So there's 2 negatives making it a positive. So we say, okay, great. That's going to converge. And this one is going to diverge. And now we say, all right, we've checked everything. We said, okay, what happens if p plus 1 is negative, positive, or 0? So p plus 1, 0 is p is negative 1. So our conclusion is it converges if p plus 1 is greater than 0, or, put another way, if p is greater than negative 1. Now, one of the things that you might notice if you compare the answer for this problem versus the previous problem, you might say, that poor function 1 over x, it just can't catch a break, can it? No, it can't. Now, 1 over x, it's kind of like a borderline case. It's right on the border between something that works versus something that doesn't work. And, well, what can you do? It's the way it is. All right, well, good. On to some more problems. This one's good. Gabriel's horn is formed by taking the curve y equals 1 over x, where x goes from 1 to infinity, and spinning around the x-axis. What is the surface area of the horn? Okay, great. All right, well, this should be fun. So, surface area. What can we do? Well, what's going on here? So, we're starting with this curve, 1 over x. Okay, but we actually don't have to take the whole curve. We're going to go from 1 to infinity. So we have this curve, y equals 1 over x, and here's 1. And we're going to take the part, this part right here, and we're going to spin it. So we're spinning it around the x-axis. And when you spin this around the x-axis, what ends up happening is you get a nice shape, and it's sort of infinitely long. And if you're familiar with what these horns look like, it does look like a very long horn, infinitely long. Gabriel, by the way, is an angel in certain religious traditions. So in this idea, he would blow his horn. So, all right, what's the surface area? Well, okay, there's a lot of horn, right? Infinitely long horn, so you might be tempted to say, well, there's a lot of surface to cover. But let's go through the math. Let's see what the math says. Now, how do you do surface area? Surface area, well, that's adding up, start to finish, 2 pi, and then you have a radius and a length. And what we think of when we talk about the radius and the length is we take a little tiny piece. So here's our little tiny piece. The radius is how far down to where we spin, and the length is that length of that little tiny piece. Okay, so let's talk about what our integral is. So for us, what do we have? Well, we're going from 1 to infinity. Okay, so 1 to infinity. Great. And 2 pi, that's 2 pi. Great, no problem. The radius, well, that's down to the axis. So that's up to the function. The curve is y equals 1 over x. So it's 1 over x. And then the length, well, that's the square root of 1 plus the derivative of the function squared. Okay, so the derivative of 1 over x is minus 1 over x squared. Okay, so there we go. There's our integral. And, well, okay, maybe we can make it look a little bit nicer. So that's the integral from 1 to infinity of 2 pi times 1 over x times the square root of 1 plus 1 over x to the 4th dx. Now, this time, you're probably looking at that and being like, oh, do we really have to integrate this? The answer is maybe not, right? One of the things we can do is ask ourselves, well, because there's an infinity involved, maybe we can do a quick comparison and say, what's true? Well, one thing that's true is, look at this piece here, 1 plus 1 over x to the 4th inside that square root. Can we say anything about that? Well, one thing we can say is this part is always bigger than or equal to 1, right? Because you see a 1 plus something, and the something is positive, so it's at least 1. Take a square root of something that's at least 1, it's at least 1. So we say, oh, well, okay, if that's at least 1, then I can bound the whole expression. Say, look, this is bigger than or equal to, and 2 pi is a constant, 2 pi, integral 1 to infinity of 1 over x. All right, well, now that's an integral we can do. So that's 2 pi, and it's actually an integral that we have done. And if you go from 1 to infinity, well, of course, when we talk about going to infinity, as x goes to infinity, what happens to the natural log as we go to infinity? Well, it gets bigger and bigger. So, goes to infinity, right? Now, normally a bound is not great at giving us an answer unless we've said, hey, it's at least infinity. And now we're like, well, then we're done. Because there's not much more you can go from there, right? If we're saying the amount of surface area is at least infinite, well, you're like, well, then that's it. I can't be a finite number if I'm more than infinity. So that's the answer. There's an infinite amount of surface area. Okay, now what's the takeaway? Well, it says you cannot take this horn and you cannot cover it in gold. There's just too much surface. There's not enough gold because that would require an infinite amount of gold. So we cannot cover Gabriel's horn in gold. Now I might say, boy, Steve, that's a very strange way to phrase this. Why would you phrase that in such a way? I sense something is coming. Okay, let's do the next one. What could that be? So, Gabriel's horn, okay, is formed by taking the curve y equals 1 over x for x between 1 and infinity and spinning it around the x-axis. Okay, yeah, that's feeling familiar here, right? Okay, so we have our curve, and we're going from 1 to infinity. We're going to spin it. And note, we're not doing a surface area here. What is the volume in the horn? Volume. So we're going to take this region here, and we're going to spin it. And so we're coming up with a solid shape. All right, so now we get to think, all right, what's going to happen here? Well, the first thing we should think about, we have volume, we have to decide a method. We have things given to us in terms of x, y is a function of x. So my natural inclination is to try that first. So that means I would slice like so, and if I spin this, I look and say what shape is being formed. And it's a disk. So we're going to use the disk method. So what is the volume? Well, the volume of the disk method, should have extended a little bit here, is what? It's adding up, start to finish, pi radius squared times your thickness. So that's the disk method. So for us, it's adding up 1 to infinity, pi, the radius, it's the height. So that's 1 over x squared dx. And now we say, whoa, what is that? Well, pi is pi. Can we integrate 1 over x squared? Yeah, we can. If you integrate 1 over x squared, see that's like x to the minus 2 power. The integral of that would be x to the minus 1, but don't forget you also need to divide by minus 1. So it's minus 1 over x from 1 to infinity. Now, plug in infinity, which means, all right, what happens as we let x go to infinity? And what happens is this goes to 0. That's cool, right? So we get pi, we're going to get 0, subtract a minus 1 over 1. So our final answer is pi. Okay, well, what does that mean? It means there's a finite amount of volume. Finite volume in this shape. So that is really cool. In particular, what can we say? Well, it says, suppose we wanted to go and actually make Gabriel's horn. Supposing we could actually do something which has this infinitely long thing. Could we do it and make it out of solid gold? The answer is yes, because we only need a finite amount of gold to make it. Now this is where we can compare and contrast the two problems, the previous problem to this problem. Because this says, look, there's a finite amount of volume, but in the previous problem, when we came here, we said, wait a second, this is infinity, so this has infinite surface area. So there's this sort of disconnect. So somehow we have something which has finite volume but infinite surface area. In terms of the gold, there's not enough gold that exists to cover it. No, we can't gold plate it because there's too much surface area. On the other hand, because it has finite volume, we could make it out of solid gold easy. There's plenty of gold. Piece of cake. And that just goes to show you, infinity is weird. Lots of counterintuitive things can be true. So that's why we want to be careful and take our time and enjoy the process, because it's such a lovely process. All right, well, let's do some more problems. On to our next one. Two-part. So part A says, look, it's an improper integral. Find the integral log x over cubed root of x dx. And then part B says evaluate the improper integral when we put in 0 to 1. Now you might say, oh, why is it improper? Well, if you look, that's extra zero-y. Well, not extra zero-y, I should say, extra improper, right? Because log, as you tend towards 0, that blows up. But also 1 over the cubed root of x, that's like 1 over 0, which is blowing up. It's really going, it's blowing up big. Wow. Okay, crazy. So, well, we got to figure out how to deal with it. So let's start with part A. Okay, so part A. So really, we can write this as x to the minus 1/3 times natural log of x dx. And usually when you see an integral that involves natural log of x, if there's not some sort of really convenient substitution, which there very rarely is, well, what we oftentimes look for is parts. Because we say, look, while we may not be able to integrate, differentiation of log, we are great at. We are fantastic at differentiating log. So we will do integration by parts. We'll set this to be u, and set this part to be our dv. So, all right, du would be 1 over x dx. And the integral of x to minus 1/3, well, you'd add 1 to the exponent. So that'd be 2/3, okay. And then don't forget that you also have to multiply by the reciprocal of the exponent. So that'd be 3/2. So 3/2 x to the 2/3. So we get uv, 3/2 x to the 2/3 log x. All right. And now subtract the integral v du. Well, so that's subtract integral. We have 3/2 x to 2/3 times 1 over x. Well, if you multiply those together, you can think of it as x to the 2/3 times x to the minus 1. That becomes x to the minus 1/3. Say, oh, well, great. We know how to integrate that. We've already done that. We know how to integrate x to minus 1/3. So we just have to do it again. So 3/2 x to 2/3 natural log x, and then minus, and here, what do we have? Well, 3/2 times, and then it's going to be x to the 2/3, and then multiplied by the reciprocal 2/3, so there's another 3/2. And of course, plus c. Or, if you like, well, let's pull out what they have in common. We can pull out an x to 2/3, that's common. We can also pull out a 3, and let's pull out a 4 in the denominator. Just 3/4. I don't like fractions. I know, that's a personal weakness of mine. Someday, me and fractions will get along great, but for now, I like to avoid it when I can. So notice, we definitely grabbed everything in the last term, so that's going to be a minus 1. Here, we didn't grab the log x. We're pulling out 3/4, but here it's 3/2, so we're going to be left with a 2 natural log x minus 1. All right, and then plus c. Okay, so great. There we go. Now, what's going to happen next? Well, we need to do part B, because that's part A. We're done with part A. And part B says now we need to do our integral. So what does part B do? Well, we have part B says integrate from 0 to 1. Okay. Now, we actually can just say, look, we know how to integrate this because that's what we did in part A. So that's 3/4 x to 2/3 times 2 log x minus 1 between 0 and 1. Now, when you plug in 1, that's very straightforward because when you plug in 1, what happens? Well, log of 1 is 0, and 1 to the 2/3 is 1. So you have a minus 1 times a 3/4. So we get minus 3/4. Subtract. Now, what happens when you plug in 0? Well, things get interesting. Why? Well, because this part is going to 0, and this part is doing what? It's getting arbitrarily large because natural log is going off towards negative infinity. So you have one part getting small and one part getting big. It's like infinity times 0. So what is that? Well, so we'll put a little note here. As x goes to 0, this goes to 0 times infinity. And we know 0 times infinity is more work. More work. Yes, if you see a 0 times infinity, it means it's indeterminate. We don't know yet. It could be a finite number, could be infinite, could be 0. There's lots of things it could be. So this is a time we say, okay, we have to be careful. We can't just plug it in because it's not so clear. It's indeterminate. Now we say, all right, let's be careful. Let's be the right amount of careful. So the way we would plug in 0 says, well, what we're really going to do is we're going to take our limit as we go to 0, and and that's as we go to 0 from above. And now, of what? Of our function, 3/4 x to 2/3 times 2 natural log of x minus 1. Okay, so that's what we need to do. Well, we want to employ tools. Now, our favorite tool when we see something that says more work is to channel our inner French and say, oh, le hôpital. Oh. Okay, so we have le hôpital in the back of our mind. Now, how does it work? Well, in order to apply le hôpital, we need to have a ratio, function over function. So we need to rewrite this in a format that allows for function over function. All right, well, that's not so bad. So there's a negative 3/4 from before. We can even pull the 3/4 out of the limit because that won't change anything. So minus 3/4. And then we're going to have a limit as x approaches 0 from above. And we want to move one of these two pieces downstairs. This part looks a lot more convenient to move downstairs because the way we move something downstairs is we take the exponent to the negative 1 power. That's very simple to move that downstairs, whereas this is going to, it's not going to look great. So 2 log x minus 1 to the negative 1 power does not look like it's going to be a fun thing to take a derivative of. So we have 2 log x minus 1 over x to the minus 2/3. Now, what's happening? Well, that's going to get large, and that's going to get large. So it's heading towards an infinity over infinity. Great. Perfect for le hôpital. So we apply le hôpital. All right. Le hôpital. And minus 3/4. And then we have minus 3/4 times the limit as x approaches 0 from above. Take the derivative of the top, and that would be 2 times 1 over x. And take the derivative of the bottom, that would be minus 2/3 x to the minus 5/3. Yes? Yeah, exactly what we would get. Well, all right. Well, we can clean that up. If we look at that, look, that's the 2's cancel. Okay, that's good. And then there's this minus 1/3. Well, look, that's a constant. Let's pull it out. Okay, so if we pull out the constants, simplify those, minus makes a plus. This 1/3 downstairs goes up to a 3. 3 times 3 makes 9. 9/4. All right, now let's talk about our powers of x. X to the negative 5/3, we move it upstairs, becomes x to the positive 5/3. So this will come up as x to positive 5/3 times 1 over x makes it x to the 2/3. That's progress. Say, look, now that's a lot easier to deal with. Very much so, because what happens? That goes to 0. So this part goes to 0, so we have negative 3/4. And we're done. Now, on a side note, you might be wondering, okay, whoops, we need to go back and fix something. Ah, so silly, so silly. I just noticed, wait a second, there was a 9 here, but that's only a 3. So what happens? Well, there should have been a 3 here. Okay, so let me just clean that up. Shh, don't tell anybody. We're all friends here, right? So, okay, so what does that become? Well, that makes it a 3 there. And so when you plug in 1, you get minus 3 times 3/4, which is really minus 9/4. And that becomes a minus 3 and a minus 3. And that's fine. We just have to update these as we go. And there we are. Okay. So, minus 9/4. Okay. Whew. All right. Back to work. Back to work. Now, why is it negative? Is that okay? You know, one of these things you should check is when you get a sign, it's not unreasonable to ask, is that the right sign? Well, let's think about what's happening here. We're going between 0 and 1, and so the denominator, the cubed root of something, will be positive. Now it comes down to saying, what about the natural log? And here we say, oh, the natural log is actually going to be a negative value as we go between 0 and 1. And so, therefore, our final answer should be negative. And so, good. Well, wow, what a problem. What a fun problem. So, there we go. There we go. Great. Well, on to more problems. Okay. Our next problem. Show that pi force is less than or equal to the integral from 1 to infinity of 1 over x squared plus sine squared of x dx is less than or equal to 1. Okay, so, that's interesting. So we have this integral, and I think we could say, and say it fairly safely, it's not a pleasant-looking integral. I don't think we could find an antiderivative for that. Not because I don't think that we're smart, I just don't think that there's a nice antiderivative. In other words, one that has a very clean form. Now that's not to say that we can't make progress, because notice it doesn't say what is the exact value. It just says, hey, let's bound this integral between two different things. Now, how can we do that? Well, we can think about what's going on. I have this function, 1 over x squared plus sine squared of x. So we can see that as x is getting big, the denominator gets small. And so it's going to 0, but it kind of has a little bit of wiggle because of that sine squared. Okay, so if we're looking to bound it, what would we want to do? Well, if I want to get an upper bound, what I'd like to do is to find some function that's above it. It's a little bit easier to manage. There's not that little wiggling going on. And if I want to get a lower bound, I'd want to do something similar, where I'd have a function underneath of it that says, hey, there's something down here. So I want to, if you will, sandwich this very inconvenient function in between two things which are convenient to work with and which we can find the answers for. So let's think about what's going on. Now, oftentimes, the critical question to ask is to say, what's important? what's important about this function? So as we look at this integral, we have the integral 1 over x squared plus sine squared of x. And if we think about it, in the long run, what's going to really drive behavior? Well, this is when we pull out the fact that, hey, we know something about sine of x. We've talked about it many times. It's not just any function. It's a function that's oscillating. It goes up and down. But it doesn't do much, right? It doesn't go up very far, doesn't go down very far. It stays in between two values. So it's only going to go between -1 and +1. So that says, look, this is bounded behavior. It's not doing very much. On the other hand, this part, it's getting huge, right? Because x squared gets big. So if I have one part that's getting big, and this other part is, it's the big part that drives the behavior. So we say, okay, great. So let's really get a nice handle on that piece. So we think about it and say, okay, well, one way we can do it is say, look, let's start with the fact that x squared plus sine squared of x. Well, let's say not even do the x squared part. Let's just do the sine squared part. What's true about sine squared? It is bounded. From where to where? Well, sine squared, it's bounded 0 to 1. Okay, so x squared is less than or equal to x squared plus sine squared is less than or equal to x squared plus 1. Now, flip everything. And what will happen is when you flip everything, you should reverse your inequalities. So 1 over x squared plus 1 is less than or equal to 1 over x squared plus sine squared of x is less than or equal to 1 over x squared. So in terms of our picture, we say, oh, this function down here, we can think of it as 1 over x squared plus 1. And on the other hand, the function on the top, we can think of this as 1 over x squared. So that our curve is going in between these two. Now, what's nice, the unpleasant part, which was unpleasant but also in some sense unimportant because of its boundedness, has gone away. There's no more sine squared. And these look like functions that we'd be happy to integrate. So we say, okay, because we've gone our bounds, it's the case that the integral from 1 to infinity of 1 over x squared plus sine squared of x dx is less than or equal to the integral of 1 to infinity of 1 over x squared, because it's on top, and greater than or equal to the integral 1 to infinity 1 over x squared plus 1, because that's underneath. All right, well, let's just follow this through. We know how to integrate 1 over x squared. It's minus 1 over x from 1 to infinity. And now, of course, when we plug in infinity, in other words, what happens as we go to infinity, and here we can see it goes to 0, right? So that's going to be 0, subtract, plug in 1, minus 1, which is 1. So our integral is at most 1. Great. We've done that part. On the other hand, integral of 1 over x squared plus 1, another integral we like, arctangent of x, as we go from 1 to infinity. Now, when we plug in infinity, in other words, as we let x go to infinity, arctangent goes to pi over 2. That's the asymptote. Subtract, plug in 1, arctangent of 1 is pi over 4, and pi over 2 minus pi over 4 is pi over 4. And therefore, pi over 4 is less than or equal to that integral. That's that part. And we're done. So this is about comparisons. And it really says, look, if we really want to bound the integral, what we really need to do is figure out what's the right way to bound the function. if we can bound the function, then we can say, all right, just integrate the pieces and do a comparison. And there you go. There you go. All right, well, on to more problems. More problems. Wow. We're so lucky we get to do so many problems. Okay. Find the length of the curve where x of t is e to the minus t over 2 times cosine of root 6t, and y of t is e to the minus t over 2 sine of root 6t, and t goes from 0 to infinity. So, what? That's a long time. What? How could this possibly be a nice number? And if you think about what's happening here, and what you can see is it looks like x is cosine and y is sine. And when you see cosine sine, you think of, oh, it's like going around the unit circle. And so we're circling around the unit circle. The difference is we have this extra e to the minus t over 2. And as we let t get large, that part gets small. So we're circling, but then we're sort of going down. So what will end up happening is we're going to start over here, and we're just going to quickly circle in. But we're going to do infinitely many. We're going to circle around infinitely many times before we hit the origin. That's a lot of times. A lot of times. And so the question is, what's the total length? Now, you might think, oh, if we circle around infinitely many times, maybe the answer is infinity. Maybe. Maybe not. We got to do the work. And who knows? Because, sometimes it's possible that infinitely many things can occur, but still only take a finite amount of length in this case. So we have to be patient. Let's work through and see what happens. Okay, so remember length for parametric curves. So length for parametric curves, you're adding up, start to finish, the square root of your x prime squared plus y prime squared dt. All right, so almost surely 90% of the work is going to become, what is this square root? If we get to that square root, we're just going to be home free. But we have to get there. So let's start doing that. Okay, so x prime squared plus y prime squared. All right, so we're going to take the derivative of x. There's two functions, so we have to do a product rule. Derivative of the first, minus 1/2 e to the minus t over 2 times the second, cosine root 6t. All right, plus the first, e to the minus t over 2 times the derivative of the second, which would be derivative of cosine is minus sine root 6t, but then of course chain rule says multiply by another root 6 squared plus y prime of t, derivative of the first, minus 1/2 e to the minus t over 2 times the second, sine root 6t, plus the first, e to the minus t over 2 times the derivative of the second, derivative of sine is cosine root 6t, and then chain rule, multiply by another root 6 squared. All right, x prime squared plus y prime squared. Good. Which becomes, now we square everything. Well, when you square here, what will you have? Well, you're going to get that term squared, so that would be 1/2 squared, would make that 1/4. E to the minus t over 2 squared would be e to the minus t. And then we're going to get a cosine squared of root 6t. All right, so that's the first term squared. And then we have the cross terms. So there's going to be a plus 2. There's a minus and a minus, so we'll go ahead and get the minuses to cancel. We have what? We have 1/2 and a root 6, so I'll write that as root 6 over 2. So that's the 1/2, the root 6. e to the minus t over 2, e to the minus t over 2 is e to the minus t. Then we have a cosine and a sine. So cosine root 6t, sine of root 6t. Okay, plus the last term squared. So that's plus e to the minus t, the root 6 squared. I should put that in front. Okay, there's the 6. That's the root 6 squared. E to the minus t comes from the e to the minus t over 2 squared. And then the minus, well, that just becomes a plus when you square it. And a sine squared of root 6t. Great. Fantastic. Okay. Now, that's x prime squared. We need to do y prime squared. We're not going to have enough space, so we're just going to write right underneath. Let's see. Here we're going to get a sine squared, so I'm going to put underneath the sine squared. Plus 1/4. We'll have e to the minus t, because that's being squared. And then sine squared of root 6t. Okay. The cross terms, well, it's going to be a minus, because that's a negative term, that's a positive term. So minus 2. We have a half times root 6. That's a root 6 over 2. E to the minus t over 2, e to the minus t over 2, e to the minus t. Then we have a sine root 6t and a cosine root 6t. Well, okay, I'll put that in the order cosine times sine. All right. And then we have this last part, which is squared. Well, square root of 6 squared would be 6. E to the minus t over 2 squared is e to the minus t. And cosine squared of root 6 times t. All right, great. Whew. Now, if we've lived a good, clean algebra life, some nice things are about to happen. What are some nice things? Well, for us, what do we see? The middle terms. See, plus, minus, and then everything matches up. They cancel out. But it gets even better. Because what do you see? Everything left has an e to the minus t, e to the minus t. You can even combine 6 plus a fourth. Well, that's 1/4 plus 24/4. So that's really 25/4 e to the minus t. And so that's 25/4 e to the minus t times cosine squared plus sine squared, which is 1. So that's it. That's x prime squared plus y prime squared. So, in case you want to see that again, I'll just say there's a cosine squared and a sine squared attached to this. But as we said, that equals 1. And so, our conclusion, our great or if you like, our sounds of happiness. Because this says, hey, the square root of x prime squared plus y prime squared, well, take the square root here. And what do you get? 5 over 2 e to the minus t over 2. So in other words, we're in great shape. So for us, return to our problem, we can say, okay, now that we've done the hard part, the rest of it is saying, okay, we're going from 0 to infinity, and our function is 5/2 e to the minus t halves. Well, okay, that's not so hard to integrate. What would that be? Well, you have 5/2 e to the minus t halves, but then you have to divide by -1/2 to account for that minus 1/2 up in the exponent, which is the same as multiplying by -2. And we're going to go from 0 to infinity. Okay, so what happens? Well, we plug in infinity. Well, what really means, what happens as we let t go to infinity? As t goes to infinity, we're going to have e to a very large negative quantity. E to a very large negative quantity is a small number. So as we go to infinity, see, this is our limit. And so this is how we're dealing with improper integrals is through the limits. So as we let t go to infinity, we see, aha, this is going towards 0. So we get 0, subtract. When we plug in 0, well, we're going to get e to the 0, which is 1. And here, 5/2 times -2 is -5, which gives us a final answer of 5. And that's it. So the total length of the curve is 5. Wow! What an answer. What a beautiful, beautiful answer. On a side note, this came from an old exam, and this was problem number 5 on the exam. So problem number 5, the answer was 5. I love it when we can do one of those fun little sort of like, cute little things. Mathematicians, of course, are known for being playful and fun. So it's a nice job. Great job. They say mathematicians, they're the best job in the world, number 1, right? So, all right. Well, I think we have time for one more problem to finish it up, a nice cool down. So, an infinitely long rod, where we have x greater than or equal to 1, has density, delta x, equals 1 over x to the a for some a above 2. And we're told that the center of mass is 5. Find a. So when we talk about rods, we think, okay, that's like a one-dimensional setting. We see, okay, center of mass, that's what the x bar means. And then we say, okay, well, what's going on here? Well, so here we're going to start. Our rod starts at 1. And if you look at our density, it's 1 over x to the a. A is a pretty big number. It's above 2. And so if you think about what's happening, it says there's a lot of mass near the start, but then as we go further on, there's less and less mass the further on we go. Okay, so it's heavier near 1, and it starts to really decay in terms of the density. But there's still mass. I mean, like you go way out that way, like, whoa, there's still a lot of rod left. There's infinitely much rod to work with. But the amazing thing is, even though it's infinitely long, the center of mass is at 5. So, in other words, if you could pick up this infinitely long rod and put it so that you had 5 resting as a point underneath, it would balance. All right. So, well, how do we do this? Well, let's talk about the formulas, right? So what is center of mass? How do you find it? So what you do, center of mass, is you do a moment with respect to 0, divide by your total mass. I like to think of it as being an averaging going on. So what's the moment? What's the mass? Well, we'll start with the mass. That's probably the easiest. You add up, start to finish, your density dx. So that's our length times density. So really the delta x dx is the mass of a little piece. And you just say, okay, well, what does that turn out to be? Upstairs, what would it be? Well, a to b of what? A location relative to 0. Because moments, you're talking about moment with respect to something, with respect to some location. In our case, we talk about, say, with respect to 0, and say, okay, so that's our location times our mass of that piece, which is our density dx. So location times density, that's our mass. All right, great. So that's how we do it. So now we know our integrals, because we know our density and we know our bounds. Okay, so this would be integral from 1 to infinity, and our x times 1 over x to the a. Well, if you clean that up, that would be x to the 1 minus a, because I can think of 1 over x to the a as x to the minus a power. dx. And downstairs, we have integral 1 to infinity of x to the minus a. Now, we know that a is larger than 2. So 1 minus a is going to be smaller than negative 1, and minus a is definitely smaller than negative 1. Which means, from work we did on previous problems, we know this integral converges. Okay, so we just say, all right, let's work this out. Well, on the top, we'd have what? Well, you'd add 1 to your exponent, and that would give us x to the 2 minus a, and then 1 over that new exponent. And downstairs, similar thing. Add 1 to the exponent, divide by your new exponent, evaluated 1 to infinity, evaluate 1 to infinity. Okay, well, that gives us what? Well, you have, when we plug in infinity, of course, plug in. I keep doing this, but I want to emphasize the point. You can't plug in where there's an asymptote, either when we talk about where we go to infinity or where the function is blowing up. But when we talk about plugging in, it means what happens as we get close. So as we go to infinity, we're going to have that number to a negative exponent. 2 minus a is below 0. So it's going to go to 0. So it's 0, and when we plug in 1, 1 to anything is 1. So it's 0 minus 1 over 2 minus a. Downstairs, same process, right? Its large number to a negative exponent goes to 0. So it's 0 minus 1 over 1 minus a. And now we say, well, great. That beautifully simplifies. The zeros, of course, go away. The minuses cancel. And you can bring that 1 over 1 minus a upstairs. So we get 1 minus a over 2 minus a. And that is our center of mass for any choice of a. Well, we know where we want our center of mass to be. We want our center of mass to be at 5. So we set it to 5. And now we're almost done. We get 1 minus a equals 5 times 2 minus a. Well, that's also the same as 10 minus 5a. Well, all right. We can do some rearranging. If we add 5a, we'd have 4a, because we have minus a plus 5a. And then if we subtract 1, 10 minus 1 would get us 9. Now divide by 4, we get a equals 9/4. And notice that this is 2.25, which is good, because we're told our number needs to be above 2, and 2.25 is definitely above 2. And so that's our final answer, 9/4. But again, we come to the idea, wow, this infinitely long thing can have a finite center of mass. So even though there's only between 1 and 5 on this side, and here there's 5 to infinity, and it doesn't make sense. Really, will it balance? And the answer is yes. That's what the math does. The math works out. It's because you have a lot more mass here, so it's more heavily biased. And even though we have some mass over there, it's very small, and it's not enough to overcome. Well, this goes to show infinity sometimes works in some counterintuitive ways. So be careful, be patient, and work through the process. But at the end, it's really the same processes. It just says, make sure you're paying attention to how you're dealing with infinity. And that's it, right? It's not so bad. Well, thanks for coming, and keep practicing. Hope to see you again. Bye.